The last video we did was exothermic reactions. So this video follows, this is going to be endothermic reactions. Endo, put in. So the big deal is this. You have to put in more energy than you get out. And once you stop putting in the energy, the reaction stops. So here is the simple equation for an endothermic reaction. A plus B plus energy yields C. That is the simplest. A plus B plus energy yields C. So in an equation, if the energy is on the reactant side, it's an endothermic reaction. And endothermic reactions, they look like this. Remember, here are the reactants, here are the products. So you have to put in energy, 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 all activation energy, and then you just get out a little bit. Okay, so here are the products, here are the reactants for an endothermic reaction. Products way up here, not very stable. In fact, it's away from the law of nature, which is nature wants everything to have minimum enthalpy. That means minimum energy. Like in 24 hours of the day, people are more stable when they have minimum enthalpy. That's when you're sleeping. So minimum enthalpy would be like this, an exothermic reaction. So if the products are way down here, that's toward the law of nature. All right, minimum enthalpy, least amount of energy, most stable. But today we're talking about the products up here. That is maximum enthalpy, and that isn't very stable at all, and it's away from the law of nature. So let's do a graph of endothermic. Here's an endothermic graph. The equation, like we just used, A plus B plus energy yields C. So the energy's on the left-hand side with the reactants. It's an endothermic reaction. You're putting in more energy than you're getting out. Plus, A plus B yields C. It's synthesis. And we'll go over these on reference table I in a couple minutes. So here's A plus B. Here are the reactants. So the very first line segment would be right here. That would be circle number 1, and that would be the potential energy of the reactants. Okay? Now, remember from the exo, the next line segment, activation energy, energy needed to break the old bonds, runs from the reactants all the way to the top. So here is the activation energy for the forward reaction, which is an endothermic reaction. From the reactants to the top. That's circle number 2, and that would be AE of the forward reaction. So circle number 2, activation energy of the forward reaction. Remember, activation energy always breaks the old bonds. That's what it's needed. If you want to break a bond, you got to put energy in. So the activation energy for this is from 20 to 90. So the activation energy for this is 70 kilojoules. So what we can write down is this. Circle number 1, that is the potential energy of the reactants. PE of reactants. And that equals 20 kilojoules. Circle number 2 is the activation energy, AE, equals from 20 to 90, 70. And don't forget, activation energy, once again, runs from the reactants to the top. I don't care if it's exo or endo. Runs from reactants to the top, and it's used to break the old bonds. So that's activation energy. Now, the next line segment is where the molecules actually collide or break apart, and it's here. It runs from the top all the way down. This is line segment number 3, and that's AC, or activated complex. So circle number 3, AC equals 90 kilojoules. Now don't forget, activated complex is at the very top, so it has the highest potential energy. It's the most unstable part of an exo or endothermic graph. The top, the activated complex. It's when the molecules are coming together. Okay? And the good thing or the interesting thing about the activated complex, I don't care if it's an endo or an exo, this is the only line segment that stays the same. Okay? Activated complex. The only line segment that stays the same for an endothermic reaction or an exothermic reaction. Runs from top to the bottom. All right, the next one is this one. This is line segment number 4. And line segment number 4 is PE of product. And that equals 70 kilojoules. And like we said, if the products are higher than the reactants, that means you put more energy in than you got out. All right? That's an endothermic reaction. And since the products are so high, they have a lot of energy, that would be maximum enthalpy. And the law of nature says everything, nature wants everything to have minimum enthalpy. Remember, that's where the products are lower, like an exothermic reaction, because they're more stable. So endothermic reactions, the products are high, not very stable, maximum enthalpy, away from the law of nature. All right, so that's that one. We haven't hit the most important line segment yet. The most important line segment is between the products and the reactants. All right, it's called delta H. And delta H is between the product and the reactant. So it would be right here. And this is line segment 5. So 5 is delta H. And remember, it's a simple little formula, P minus R. So in this case, products is 70 minus 20. So it would be 70 minus 20, and that would give us a positive 50. Positive 50 kilojoules. So now we know this. If delta H is a positive, the reaction is endothermic. So that's the most important. And another name for delta H is heat of reaction. So remember, it's between the products and the reactants. Heat of reaction, P minus R. And we're going to get into table I in just a couple minutes to show you the positive and negative delta H's. But we got a couple more things to do here. There is another line segment that we don't have on here, and that's this one. That's line segment number 6. So what would line segment number 6 be? It would be the activation energy for the reverse reaction. So line segment 6 is AE, which stands for activation energy for the reverse reaction. So line segment 6, AE of reverse reaction. Now remember, I said activation energy runs from the reactants to the top. Well, since this is the reverse, that would be the reactant. So it's reactant to the top. And that equals from 70 to 90, that's equals 20 kilojoules. So number 6 is the reverse reaction for activation energy for an exo. Number 2 is the activation energy for an endo. So here is the graph. Now we have to do a couple things. What if we put a catalyst into this reaction? Remember, there's about 6 things to increase the rate of a chemical reaction, and to do that we got to make more collisions. So if we increase the temperature, more collisions. If we increase the pressure on a system of all gases, we increase collisions, increase the rate of reaction. Increase surface area, increase the rate of reactions. Okay? If we add more concentration, increase collisions, increase rate of reaction. And if we don't have too many bonds to break in the reactants, that will make the reaction go faster. Now the last one is if we add a catalyst. Now, a catalyst speeds up both forward and reverse reaction rates without itself being used in the process. So how does it speed it up? It knocks down any line segment that goes to the top. So what line segments go to the top? Activation energy of the forward, activation energy of the reverse, and the activated complex. So here's what a catalyst would do. It would a catalyst lowers the activation energy. So you don't need as much energy to make the reaction work. So any line segment that goes to the top of the graph gets knocked down. Once again, activation energy of the forward, activation energy of the reverse, activated complex. But the most important thing that a catalyst doesn't do is a catalyst never, ever, ever touches this one. A catalyst never touches delta H. That is a pretty good one. That's always on a test. All right? Catalyst never interferes with the delta H. Now, next couple things, couple trick questions. If we subtract the activation energy of the forward reaction from the activation energy of the reverse reaction, we always get this. So when we subtract the AE of the forward from the AE of the reverse, we get delta H. Great test question. Now, another question that will probably be on there. What 2 line segments from the exo reaction will produce the activation energy for the endo? What 2 line segments do we have to add together from exo till we get endo's activation energy? Well, here's endos right here. So what 2 line segments do we have to do? Well, we got to do delta H and we have to do the AE. So to get the activation energy for an endothermic reaction, we would have to add the delta H and the activation energy for the exo. So those are some pretty good test questions right there. Now, endothermic reaction, like I said, it's like melting ice. You put heat in it to melt the ice, but once you stop the heat, the ice stops melting. So you have to continually add energy, and once the energy stops, the reaction kind of stops. Now, I'm going to show you one that we did in class. This one right here. That is ammonium nitrate. This is ammonium nitrate, all right? Ammonium nitrate, it looks like crystals, and if it looks like crystals, chances are it's an ionic compound. Now, for this particular reaction, ammonium nitrate yields ammonium plus nitrate. This is a decomposition reaction. It's breaking apart. Now, over here, look, it says plus 25.69. which means if the delta H is positive, the reaction is endothermic. And what I showed my kids is I put some of this ammonium nitrate in water, stirred it up, and had them feel the bottom of the beaker. And it felt cold because in order for this reaction to work, you have to add energy. And if you don't add energy, the reaction stops, doesn't work. So when they put their hand on the bottom of the beaker, it felt cold because energy was being sucked from their body temperature and the temperature of the water to make this reaction work. And once they took their hand away, and if I put this outside in the freezing cold, there's no more heat to be absorbed, the reaction would stop. So, endothermic reactions, they need energy put in order for them to work. Once the energy stops, then the reaction usually stops also. All right, so if something feels cold, a reaction feels cold to you, it's an endothermic reaction. And then the reverse is true. If there's a reaction and you feel the test tube or beaker and feels hot, that means energy is being given off. That's an exothermic reaction. So, this is a perfect example. Now, what you can do is, this is the decomposition of ammonium nitrate, and that's a positive delta H. But what about the synthesis? Synthesis goes this way. So we add nitrate and ammonium, and we make ammonium nitrate. And if we're going the opposite way on this table I, then we have to change the sign of delta H. So the reverse reaction, the synthesis of ammonium nitrate, would be an exothermic reaction because that would be negative 25.69. So this way is synthesis, exothermic, negative.
I don't have an answer for that. Is there something else I can help with?
This is decomposition, and it's going the proper way from left to right. So it will be positive 25. That means it's an endothermic reaction. Okay, so on this chart, you can see there's a couple endothermics. And the deal is this.
I'm not sure I understand.
So the deal is, the higher the positive number, the higher the products are, the less stable they are. Maximum enthalpy. So let's see which is the least stable products. Here's a pretty good one. The synthesis of C2H2, which is acetylene, is a positive 227. So chances are it looks like this with the products way up here. They're incredibly unstable, away from the law of nature, max enthalpy. That's what that means. So this one on reference table I, the synthesis of C2H2 is probably the highest and the most unstable products formed on this whole chart. So we're going to do a couple equations from reference table I. So here's the first equation. N2 plus O2 yields NO2. And when you look at that, it's not balanced. So the first thing we have to do is balance it. I have two N's there. So what we have to do is we have to put a 2 right there. But that 2, don't forget, blows through all of the elements. So I have 2 N's, but I have 4 oxygens. So I have to put a 2 here. All right? Now, what it says is this. Delta H equals a plus 66. Delta H equals a plus 66 for that reaction. Okay? So, if it's a plus 66, that means delta H is positive. Positive means endothermic. Endothermic means you have to put the energy on the reactant side. So that plus 66 would look like this. 66 kilojoules plus. So that is what this reaction would look like. Okay? So this is a synthesis, It's an endothermic because delta H is positive. Now, what if I wanted to find the delta H for the formation of just one NO2? So, watch. Okay, so what this means is, what is the delta H for one molecule of NO2 formed? Well, 2 NO2s equals a plus 66. So obviously, if I only want to know how much delta H for one molecule of NO, I cut it in half. So the delta H would equal a plus 33 per molecule. Plus 33 per molecule formed. That's what that means. Now don't forget, those arrows means it's a reversible reaction. So going this way, if I went this way, that is decomposition, and I'd have to change that plus 66 to a minus 66. So for this exoendo test, you have to know if the reaction is going forward or reverse. If it's going forward, you keep delta H's sign the same. If it's going reverse, you got to switch the sign. So that's one of the reactions we're going to do. So let's do another reaction from reference table I. Carbon plus hydrogen gas yields C2H6. So obviously that's not balanced. There's 2 carbons. I got to put a 2 here. And there's 6 hydrogens. I have to put a 3 here. Now, as I look at that, the delta H is this. The delta H is a negative 84 kilojoules. Okay? So what that means is, if it's a negative delta H, that means it's an exothermic reaction, and the energy has to be with the products because exo means given off. So it's a negative 84, but you don't put negative in the equation. You just go like this, plus 84 kilojoules. So remember, if it's a negative delta H, it's an exothermic reaction, you got to put the energy on the product side. If it's a positive delta H, you put it on the reactant side. But here is the reaction. And this right here is synthesis, C2H6. Synthesis of ethane, C2H6. Now, if I just gave you that equation and said what was delta H, you'd go, oh, well, the energy's on the right-hand side with the product, so delta H would be a negative 84 kilojoules. And then if I said, how much energy would it take to make 2 molecules of C2H6? 2 molecules of C2H6, you just double it. So it would be 168. So that's how much energy you would have to put in to make that reaction work. If I wanted to make double the amount of product, you double the delta H. If I wanted to make half the amount of product, you cut it in half. So this is going this way, it's synthesis, and it's a negative delta H because energy's there. But going the opposite way, that would be decomposition, and what that means is this is the reactant, there's the energy, this is decomposition, and this would be endothermic. So going this way, the delta H would be a positive. Okay? Hope you understand these equations and endothermic reactions.